Okay, hi everyone. This video is going to focus on the topic of intermolecular forces. And there are three different types of intermolecular forces: hydrogen bonding, dipole-dipole interactions, and London dispersion forces, which we often call LDFs. So let's go ahead and get started. Okay, so the first thing I want to do is clarify the difference between intermolecular forces and intramolecular forces. So they're very, very similar, just that two-letter difference there. So make sure you pay really close attention to what you're seeing. Normally, it's always going to be the intermolecular forces you'll see, but make sure you keep the ideas separate in your mind. So whenever you see intermolecular forces, kind of the analogy for that is an interstate, okay? So that highway that goes across state lines connecting different states together, versus intramolecular forces, kind of like intramurals, which if you start to look at colleges, you'll see those are sports teams that play within one school. So maybe if you go to Ohio State and you're not good enough to make the Ohio State basketball team, but you really like it, maybe you get on the intramural team for your dorm or for your major or something like that. So intramurals within a school, interstate across state lines. So intermolecular forces act between two different molecules versus intramolecular forces are within one single molecule. So intermolecular forces, as I already said, include hydrogen bonding, dipole-dipole interactions, and London dispersion forces. Intramolecular forces, we've already talked about these. They were just called bonding in that case. So it's ionic, covalent, and metallic bonding are intramolecular forces. Intermolecular forces are the new thing. And then intermolecular forces, overall, they're weaker. Doesn't mean that they're not important. They're just not as strong as the intramolecular forces. Okay, so let's go ahead and first talk about hydrogen bonding. So hydrogen bonding occurs whenever a hydrogen bonds directly with either an oxygen, nitrogen, or fluorine atom. This creates a very polar covalent bond. And when this happens, the hydrogen has a partial positive charge, and that other atom, whatever it is, the fluorine, oxygen, nitrogen, has a partial negative because those are all highly electronegative elements. And the idea here is the partial positive end of one molecule. So the hydrogen end of one molecule is going to be attracted to the partial negative end of another molecule. So that fluorine, oxygen, or nitrogen. So a little tip to help you remember hydrogen bonding is phone plus H. So the way I always remember it is E.T. phone home. Okay, that classic movie E.T. where little aliens trying to contact his home planet. Well, use that analogy for hydrogen bonding. In this case, our phone, we're going to misspell it, F-O-N. So F-O-N, and then home stands for the hydrogen. Now, if you think about this, if you have a phone and you have a home, but they're not connected to one another, you can't make contact. So you need your phone, your fluorine, oxygen, nitrogen directly bonded to your hydrogen. And this is the strongest out of all the intermolecular forces. So if you look at the pictures down below, on the left, I have two water molecules, okay? And the partial negative of the oxygen in the water is has a little dash line showing an attraction between the partial positive of the hydrogen. Now, one thing I want to point out, hydrogen bonding is not a bond, okay? It's a really, really bad name. I know it's not a bond. It's just an attraction. That's how we show the dashed line between the oxygen and the hydrogen with the two separate molecules. They're not bonding. They're just attracted to one another. And then between ammonia molecules, picture on the right, the nitrogen and hydrogen, again, are attracted, so we have that dashed line. The next type of intermolecular force is dipole-dipole interactions, and this occurs in any molecule that has a polar bond and a polar shape. Okay, so we need overall a polar molecule. Okay, we need both the bond and the shape to allow for polarity, so we need a polar molecule. And just like hydrogen bonding, partial positive end of one molecule attracts to the partial negative end of another molecule. Now, dipole-dipole interactions are going to be weaker than hydrogen bonds because these bonds are less polar than the hydrogen bonds. Fluorine, oxygen, and nitrogen are the most electronegative elements we have. So when they bond with hydrogen, we get a very polar bond. All other polar bonds are still polar. They're just not as polar. So that's why they are weaker than hydrogen bonds. So if we look at these two pictures, on the left, we have a polar bond between the carbon and the oxygen, and we overall have a polar shape because it's not completely symmetrical. So that creates that dipole-dipole interaction. So you could kind of draw that imaginary dotted line between the carbon on top of the blue delta to the oxygen right below it. And then on the right, hydrochloric acid that we see on the right, we have that dotted line showing the dipole-dipole interactions. Again, intermolecular forces are not bonds, okay? And then the final type of intermolecular force we have is London dispersion forces. So this is based upon the idea that we have the nucleus with the electrons circling around the outside. And on average, the electrons are evenly arranged around the nucleus. But at a specific instant in time, if we could freeze things, the electrons could clump up on one side of the atom. And when that happens, we have one part that's a little more negative and one part that's a little more positive. That's from the fact that electrons are negatively charged, and the nucleus, which has protons and neutrons, overall has a positive charge. So if we look at that picture down below, the left shows what we have on average. The right half of that picture shows what we have in a specific instant. So if we have the electrons all on one side, the nucleus on another, that gives us that instantaneous dipole, partial positive and a partial negative. Now, if one atom has an instantaneous dipole, it can actually influence its neighbors to also have instantaneous dipoles. And that's what you see in the picture down below. So that blue and red atom, that one forms its instantaneous dipole first, and then it's going to impact its neighbors. Now keep in mind, opposites attract. So the positive of one is going to force a negative in the other. Now, London dispersion forces are the weakest intermolecular force because they're based on those instantaneous dipoles, which are temporary, and they only last a very, very short period of time. However, London dispersion forces are still important. That's because every single atom and molecule has London dispersion forces because they have electrons and they have a nucleus. So they are the most common intermolecular force. And then the thing I want to point out, when comparing London dispersion forces between different molecules, the bigger the mass, so the more protons, neutrons, and specifically electrons that an atom has, the stronger their intermolecular forces. Okay, so the bigger the molecule, the higher their atomic masses, the more intermolecular force it will have. Okay, so if we look at these examples, let's go ahead and break them down. So for hydrogen bonding, we need our phone, fluorine, oxygen, or nitrogen, and it needs to be directly bonded to a hydrogen atom. Okay, so they need to have a line going between the fluorine, oxygen, and nitrogen directly to a hydrogen. And this is the strongest intermolecular force. Dipole-dipole interactions, we just need a polar molecule. So a polar bond and a polar shape, and they are intermediate in strength. And then London dispersion forces, all we need are electrons. So pretty much every single atom has London dispersion forces, and these are the weakest. So this part is not necessarily in your notes, but it might be good to kind of help you out as you go through these examples and work through them. So you might want to write these down or take some quick screenshots. So some questions to ask yourself as you determine the intermolecular forces. When it comes to hydrogen bonding, you want to ask yourself, is there a fluorine, an oxygen, or nitrogen in my compound? If there's not, you don't have hydrogen bonding. If you do have one of those three atoms, you next want to check and see if a hydrogen is bonded to it. So is there a line connecting a hydrogen to a fluorine, an oxygen, or a nitrogen? If you say yes to both of those things, you have hydrogen bonding. For dipole-dipole interactions, you first want to ask yourself, does your molecule have a polar bond? Now, specific thing here, we want to see if it's something other than a fluorine, hydrogen, oxygen, hydrogen, or nitrogen, hydrogen bond. That's because those three things mean that we have hydrogen bonding and we don't want to double dip. So, does my molecule have a polar bond? And does my molecule have a polar shape? Okay, if we say yes to those two things, we have dipole-dipole interactions. And then finally, for London dispersion forces, we ask ourselves, does my molecules have electrons? Pretty much 99.99999% of the time, you're going to say yes. So if so, then you have LDFs. Okay, so let's go ahead and work through some examples. So what type of intermolecular forces does methane have, CH4? So we first want to think about hydrogen bonding. So is there a fluorine, oxygen, or nitrogen atom in my compound? So I look, well, I have carbon and hydrogen. So the answer is no. Because I've already said no once, I don't even need to go on to question 2. I know this one does not have hydrogen bonding. Next question. Does my molecule have a polar bond other than one of those 3 things? Well, between carbon and hydrogen, I want to think about their electronegativity values. Carbon is 2.5, hydrogen is 2.2. So if I subtract those, I get 0.3, which is not polar. So no, it doesn't have a polar bond. So again, because I've said no once, I do not have dipole-dipole interactions. And then finally, does my compound have electrons? Yep. So methane, CH4, has the intermolecular force of London dispersion forces. Okay, let's try another one. What type of IMFs does methanol have? Okay, so that molecule down below. So is there a fluorine, oxygen, or a nitrogen atom in my compound? Yeah, there's an oxygen. And then the next question, is that oxygen bonded to a hydrogen atom? Yeah, there's a line directly connecting the two. So because of that, I have hydrogen bonding. Next question for dipole-dipole. Does my molecule have a polar bond other than the fluorine, hydrogen, oxygen, hydrogen, or nitrogen, hydrogen? In this case, no. Okay. So does my molecule have a polar shape? Well, it doesn't matter. I don't have dipole-dipole interactions. So the next one, LDFs. Does my compound have electrons in it? Yep. So I have LDFs. The one thing I want to point out, yes, this molecule is polar, but it's polar because of the oxygen-hydrogen bond. So because of that, I don't say I have both hydrogen bonding and dipole-dipole interactions. Okay, if you have questions on that, please let me know. And then finally, what type of intermolecular forces does carbon tetrafluoride have? So is there a fluorine, oxygen, or nitrogen in my compound? Yeah, I have 4 fluorines. Now, is that fluorine bonded to a hydrogen? No. So because of that, I do not have hydrogen bonding. If you don't have a hydrogen, you can't have hydrogen bonding. Next thing, does my molecule have a polar bond? Okay, so carbon, fluorine. Fluorine is 4.0 for its electronegativity. Carbon is 2.5. So that is a difference of 1.5. So yeah, it has a polar bond. Does my molecule have a polar shape? Well, this is a tetrahedral shape, so it's going to be symmetrical in all directions. So no. Okay, my molecule has a polar bond, but it does not have a polar shape, so it's not a polar molecule. So because of that, I do not have dipole-dipole interactions. And then finally, LDFs. Does my compound have electrons? Yep. So LDFs are at go. Okay, so final question. Rank the molecules according to their relative strength of their intermolecular forces, from the weakest to the strongest. Okay, so we have methane that only has London dispersion forces. We have methanol, which has hydrogen bonding and LDFs, and then carbon tetrafluoride, which only has LDFs. Well, we know methanol is going to be the strongest because hydrogen bonding is the strongest. So that one's going to be the last one. But we need to compare methane and carbon tetrafluoride. Okay, so remember that tip. The mass that is higher will have the higher LDFs. So we look. Carbon's the same for both of them. But on methane, I have 4 hydrogens. Well, hydrogen's as small as you can get. okay, versus fluorine is much heavier. It has a molar mass of 19. So if we compare that, carbon tetrafluoride is going to have the higher mass for its compound. So because of that, it's going to have stronger LDFs. So if I rank them from the weakest to the strongest, I go from methane to carbon tetrafluoride to methanol. So I hope that helps. If you have any questions on this, please go ahead and let me know. Otherwise, have a great day, everyone, and I'll be talking with you soon. Bye.